How does microstructure influence material performance in tests? Imagine looking at a tiny world inside a piece of metal or plastic, where grains, phases, and defects shape how it behaves. That's what microstructure is all about. It's the arrangement of tiny features inside a material that you can only see under a microscope. This internal setup has a big impact on how the material performs during tests and in real life. When engineers design tests for materials, understanding microstructure helps explain why a material might crack, bend, or last longer. The size and shape of grains, which are the small crystals making up most metals, play a key role. Smaller grains usually make a material stronger because they block the movement of dislocations, which are tiny defects that allow deformation. But if the grains are too small, they can also create more grain boundaries, which can be spots where cracks start. Different phases within a material, like hard particles embedded in a softer matrix, can improve wear resistance. However, these same phases can also cause stress concentrations, making the material more likely to break under certain loads. Defects such as voids, inclusions, or areas where elements have separated can act as weak spots. These stress concentrators often become the starting point for cracks or corrosion. Changes in how a material is processed, like how fast it cools or how it is welded, can alter the microstructure. For example, rapid cooling can produce smaller grains, while slow cooling might lead to larger grains and different phases. These changes directly influence how the material behaves during testing. When conducting failure analysis, microstructure analysis helps explain why a part failed. By examining fracture surfaces with tools like optical microscopes or electron microscopes, engineers can see where cracks started and how they grew. Ultrasonic testing can detect variations in grain size or phase distribution, giving clues about the internal structure. This information helps identify if failures come from manufacturing flaws, environmental damage, or unsuitable material choices. Knowing the microstructure guides improvements in material design and processing. For example, adjusting heat treatments can refine grain size or modify phases to make a material tougher or more resistant to corrosion. In industries like aerospace or construction, microstructural evaluation ensures materials meet safety and performance standards. It helps decide on the right heat treatments, welding procedures, or material substitutions to improve durability. In the end, microstructure controls how a material responds in tests by influencing its strength, toughness, and resistance to failure. Analyzing these microscopic features reveals the root causes of problems and helps develop better materials. This understanding is essential for preventing failures and making products that last longer and perform better in their everyday use.